Hello, welcome back. This is Calculus by Dr. Oz. We're continuing with Chapter 2 sections, and Chapter 2 is all about limits and their properties. And in fact, today we're going to go over the very last section of Chapter 2. It's about infinite limits. We have two course learning objectives to achieve for this section, and the first one is what we're going to do in this video. We're going to determine infinite limits from the left and from the right, and that's going to allow us to pinpoint the vertical asymptotes of the graph of a function, if there is any vertical asymptotes, obviously. So vertical asymptotes are all about infinite limits, and that's going to be the second learning objective of this section. All right, let's consider the function f of x equals the rational function 3 over x minus 2. You can go ahead and graph this function. We're going to show that as you get closer and closer to 2 from the left, the values of f decreases without bound. And as you are on the right of 2, that means you're approaching 2 from the right, as you see that the function values get bigger and bigger. In other words, f increases without bound. So we have infinite limits going on here, but we want to also see this by a table of sample values. So our target point, limit point is 2, and we're getting sample points on the left and on the right of 2. On the very left, we start with 1.5, we choose 1.9, 1.99, and 1.999. And on the right, you have 2.001, 2.01, 2.1, and 2.5. And you can choose other sample points if you wish. And now what you're going to do here is to evaluate the function at each sample point by using your calculator if you want to. And I want you to pause the video at this moment and bring up your calculator and punch in f of 1.5, f of 1.9, and all the way to f of 2.5. And check for pattern after all. So essentially, when you get closer to 2 from the left, the function values decrease without a bound because you start with -6 and then jump down to -30 and then -300 and -3000. And if you choose another sample point like 1.999, you're going to go to -30,000 and on and on and on. And on the right, you start with 6, increase to 30, 300, 3000, 30,000, 3 million, 3 billion. If you get closer and closer to 2, that means f increases without a bound. And as you see here that we use the two primitive approaches of looking at the limit of a function. One is the table of simple values, and then the other one is the graph of the function, essentially to see where the function values approach. So now we're going to use a notation for that. So if you approach this rational function as x approaches 2 from the left, so this is like x approaching 2 from the left. So remember that f was decreasing without bound, so the limit value is going to be -infinity. In the past, we called this limit to be doesn't exist, so now we're sort of like quantifying that, and we're just saying like it's -infinity. And if you get closer to 2 from the right, let me just write bigger here, okay? If you approach 2 from the right, then the function values increase without bound, so we represent that limit to be infinity. And obviously infinity and -infinity are not real numbers. These are just symbols showing that these are like big numbers. So this is the formal definition of limit, and I can tell you that neither sections 136 or 136 honors are responsible for this. I'm going to skip this part, but if you're interested, please read it out in your own spare time. All right, let's go through this example number 1, which is determining infinite limits from a graph. So we have two different functions provided to us. One is 1 over x minus 1 quantity squared. The other one is -1 over x minus 1. And we're checking the limits as x approaches 1 from the left and from the right. Let's try to determine those limits by looking at your graphs. As you see that if you get closer to 1 from the left, the corresponding function values increase without a bound. So that means the limit on the left is going to be infinity. And if you're getting closer to 1 from the right, the corresponding function values, again, increase without a bound. So we can perfectly tell that both left and right limits takes you to infinity, so is the limit of the function at x equals 1, that's equal to infinity. And you can easily recognize here that x equals 1, the line, the vertical line x equals 1 right here, is a vertical asymptote. And how about part B? So if you get closer to 1 from the left, as you see, the function values increase without a bound. So the left limit is going to take us to plus infinity. And if you go in this direction instead and getting closer to 1, so you're walking all the way down here, so the function values decrease without a bound. So the limit is going to be negative infinity. And here are two limits by using the notation of one-sided limits. One is negative infinity and the other one is plus infinity. And as you can see that x equals 1 line, vertical line, is a vertical asymptote for this function. In this video, we determined infinite limits from the left and from the right by looking at the table of sample values or the graphs of functions. And we also mentioned about vertical asymptotes, but we didn't really define it. So in the next video, you're going to see how we're going to find and sketch the vertical asymptotes of the graph of a function. So for that reason, I'll see you in the next video. Bye.